Laboratory. He is currently an assistant professor of mechanical engineering at Stanford University, and he received his bachelor's, master's, and PhD degrees from Princeton University in mechanical and aerospace engineering. You might have remembered him from when he was here from 2019 to 2022. And please be advised that this talk is being recorded, and also it's an unclassified meeting, and be aware of any export control issues. And if you have a question, please make sure I give you the microphone so people online can hear you. And if you're online, please enter your questions in the chat field. Otherwise, I hope everybody enjoys, and please take it away.
Sure. Okay. Am I properly on now? Great. Fantastic. So it's good to be back again. I'm going to talk today about work in the area of plasma optics. So this is broadly taking advantage of what we know about plasma, about light, to build or try to build lasers that go beyond the capability of what we can do today with systems like NIF, with systems like the 10 petawatt laser at Eli, and think about what it will take to build lasers that can go beyond the capabilities of solid state optics. So we know that we can build big lasers, and Livermore can build big lasers. Some of the highest energy and the highest power systems that we have available to us are really big, like NIF, like the petawatt beams, where the sizes of all our optics are large, tens of centimeters to up to meter scale. And the particular problem that this poses for us, if we think about doing things like higher intensity science or ICF experiments at rep rate, is that we have a damage problem. Our optics can't tolerate more energy or power without either getting larger or being made of some material that can tolerate higher damage fluxes than any solid material, glass or metal, that we're currently aware of. So this leads us to plasmas as a material for controlling light. So sorry. What we are trying to do is avoid things like this laser damage image on the left side. And we're going to do that by using materials that don't get damaged, like glass. So the idea is that instead of using solid state optics that are limited when we're talking about sort of femtosecond duration laser pulses to peak powers of, or peak intensities of 10 to the 12 watts per centimeter squared, about a terawatt per centimeter squared, we're going to plasmas where the damage thresholds can be 100 or 1,000 or 1,000,000 times higher than what solid state optics can tolerate. So we're interested in plasmas as an optical material because they're damage tolerant, and also they have some secondary advantages, which is that they tolerate ultra fast responses, so we can use them for control of femtosecond pulses. Plasmas tend not to be wavelength specific, so we are not limited to particular wavelengths in the same way that we are for certain, the gain medium of a laser, for example. And they also give us access to some extreme nonlinearities. So there's the opportunity to do things like very efficient, extremely high power frequency conversion. So plasma optics is a big field with lots of new things happening in all the time. And this ranges from things like cross-beam energy transfer for ICF, so this control of energy between different beams in a Hall room is one very successful form of plasma optics. Another standard existing plasma optical component is the plasma mirror, which are used as a standard way of cleaning the temporal contrast in high power femtosecond beamlines. But there are many other proposals out there to try and replace the other optical components that we rely on when it comes to high power lasers. So this includes plasma amplifiers, so using stimulated Raman or Brillouin scattering in a plasma to try and build an alternative to the combination of a crystal, a gain medium, and a compressor, making plasma gratings and photonic crystals, so manipulating light with this kind of diffractive optic, various types of plasma lenses, and some of the beam combiner work that's been done here. The fundamental problem that we face as we try to work with plasmas in this way is that plasmas are difficult to make with optical quality, and they're difficult to control. And so in general, we want methods for making plasma optics that are robust to imperfections in the plasma that we're creating, that aren't going to be too sensitive to things like variations in temperature and density, and try to avoid some of the plasma regimes that are difficult to get a handle on, kinetic regimes, regimes with severe instabilities, and so on. And to give you an example of this, so one of the methods for using plasmas to manipulate light is parametric plasma amplification, so Raman or Brillouin amplifiers. It's a really nice theory and computational problem. The issue that we face as we try to do something like this in experiment, the simulation shows this really nice amplification process as a pump beam crosses a probe beam in a plasma, so that probe pulse gets amplified to some kind of extreme intensity. But in experiments, even in the best case, the beams that come out of this are extremely poor quality and messy. And generally, the conversion efficiency in experiment is far lower than what theory and computation would expect. And part of the issue here is that we're relying on this stimulated scattering process. It is a relatively complicated process in the scheme of things, and it is quite sensitive to plasma conditions. So when we try to implement an amplifier like this, we often, especially for short pulse lasers, run into some serious issues with how well it works and how useful that beam that comes out actually is. So in sort of the best case, you might get a beam that looks like that top right image, which is not really ideal if you want to eventually get a high quality focal spot that lets you take full advantage of all that power to get to high intensity. So instead, the approach that I'm going to talk about today is something that we'll call diffractive plasma optics. And here we are trying to mitigate the effect of some of these plasma imperfections and instabilities by taking an approach that relies on the linear optics of plasma rather than a nonlinear interaction. And the way that we do that is that we're separating this optic formation process, which you can see on the left, the two beams that are creating some kind of index modulation in a plasma, from the application of this process, which is this probe beam crossing a grating, and this is entirely a linear optical effect. So it is not the propagation of this probe beam, provided that the probe is not so high intensity that it's above the damage threshold for a plasma, can be treated mostly linearly. We're not relying on some kind of nonlinear action to get control over this beam. So today's talk, I'm going to go through some of the theory of these diffractive optics, our understanding of how they should behave. I'll then spend some time talking about how we observe that they behave in the laboratory and an experiment. And finally, I'll talk about some of the applications that these plasma optics enable. So first with the theory. Diffractive optic, what I mean by this in this context is that we have some kind of optical material with an index modulation or a change in index on a length scale comparable to the wavelength of light we're trying to control. So we have some kind of periodic change in the index of refraction, and that allows us to diffract a beam. So this could look like the diffraction gratings that you're familiar with, the reflection gratings that are in a compressor. what we are going to be working with are volume gratings. So you can imagine this as some volume in a material where there's a one-dimensional modulation and index of refraction. If a beam of light is incident at the Bragg angle on this optic, it will be diffracted. If it's not incident at the Bragg angle, then it won't be efficiently diffracted. So we can think about putting together volume Bragg gratings in a few different ways. If we have just sort of an arbitrary spread of index of refraction, we'll have curved boundary conditions or irregular boundary conditions. And this kind of grating is in general extremely difficult to evaluate, requires numerical evaluation to sort of look at an arbitrary grating. The two simpler cases are reflection gratings and transmission gratings, and these are distinguished by whether the beam that is diffracted comes out the same side as the beam that was incident of your grating, or it goes out the opposite side. And they may seem like they're pretty similar apart from the boundary conditions, but this does have some important impact on both the efficiency and the behavior of the beam that comes out of its grating. So, for example, a reflection grating goes, its efficiency goes as the hyperbolic tangent of the sort of the strength times the thickness, which means that it goes towards 1 as your grating gets thicker. Transmission grating, if you make the grating thicker, your efficiency oscillates. Beams switch back and forth between the diffracted and undiffracted beam. A reflection grating is a little bit like a dielectric mirror, but a transmission grating is dispersive. It will split light up depending on the wavelength that comes in. So we're going to focus on building transmission gratings because we have more applications in mind that require this kind of interaction. So the efficiency of a transmission grating, we can write it down. There's an expression that looks like this, where kappa is a measure of the grating strength. It is directly determined by the modulation of the index of refraction that we can achieve. So because in a plasma index of refraction is related to density, this generally means that we're talking about achieving some kind of modulation in density. We have the grating thickness, which is relatively straightforward at D, and this parameter B, which represents the mismatch of the grating. So if you're at the wrong wavelength for your angle of incidence, or there's some other issue with your grating, then you'll have B and you won't be able to get 100% efficiency. But with an ideal grating, we can, at least in theory, get 100% diffraction from a transmission grating like this, subject to some constraints. Obviously, in experiment, we don't necessarily we do not expect to get 100%, but it is good to know that our sort of theoretical limit, our best case, does not constrain us here. So to give you a sense of what happens when a beam is not at the Bragg angle, as we move away from the Bragg angle, the efficiency of our grating starts to drop, as shown by this red curve here, and we also get dispersion. So if we change the wavelength of our incident beam, but not the angle of incidence, then the light that's diffracted will be dispersed at some range of angles. We have the ability to sort of match up the simulations that we have for this process and the theory very closely. So we have some confidence that, at least from the theoretical side, we understand how this kind of grating works. So the question is, how do we make one that takes advantage of the properties of a plasma? One of the reasons that we're interested in this kind of grating is because plasmas are not ideal, and they are pretty insensitive to grating properties that are not perfect. So for example, you're seeing here lines efficiency calculations for different grating sort of strength times thickness products for a variety of different shapes of grating. So it doesn't actually matter whether we've created a grating with a perfectly rectangular profile or some kind of trapezoidal profile or something fairly irregular. the expected performance is actually pretty similar, almost indistinguishable, as long as we don't have structure that's sort of comparable to the wavelength. We can tolerate fairly large fluctuations in overall grating density. So we might imagine that if you were trying to create a grating in a gas jet, the fact that you have substantial gradients on the sides of your gas jet isn't necessarily a problem for this kind of optic. So this sort of resilience is very useful for creating an optic that's actually useful. Because what this looks like, if we create a grating, is that we're going to take two pump laser beams and cross them to create an interference pattern, something like in the top right image. If we have a mechanism that maps the intensity of this interference pattern to the index of refraction in our medium, then we can create an optic. So that leaves us with a couple of choices. One is, what is the best way to map intensity to index of refraction that takes advantage of the properties of a plasma? And what's the best way to restrict the overall geometry of the system? So we know that plasma refractive index is directly related to the plasma electron density. So in a plasma, this means that modulated refractive index means modulated electron density. We have a few different ways that, at least in principle, will allow us to do this. One is ionization. So what this process involves is interfering two beams. If we've chosen the intensity of our beams such that regions of constructive interference are above the ionization threshold and regions of destructive interference are below it, we're going to create a plasma, but only in the regions of interference. So we'll get layers of plasma and neutral gas that are spaced by 10 microns or so. And this is an image, an experimental image of what the fluorescence from a structure like that looks like. And so this works as a grating because plasma and neutral gas at the same density don't have the same index of refraction. So we've created our modulated index of refraction over some volume. We can also use the ponderomotive force to generate electron and ion fluctuations and create strong modulations in a fully ionized plasma this way, which is a little bit similar to CBET, except that our pump beams are not, they're at exactly the same frequency. They're not detuned from each other. So this is a static grating. It's not moving around. And the final approach that we have explored is something a little bit different. It actually doesn't involve plasma at all. It's purely a gas effect. So we can create strong modulations in neutral gas density. And for the same, for the reason that index of refraction of a gas directly depends on its density, if we have a modulated gas density, we can also create a grating. So these gratings have, we do not have the same magnitude of index modulation available to us. So they're a little bit less suited for femtosecond beams, but they have longer lifetimes. So this kind of grating is well suited to the narrower spectrum and longer duration of a nanosecond pulse or a NIF-like beam than the other mechanisms. So the experiments I'm talking about today are based on ionization. So we're going to take a couple of different approaches to create an ionization grating. The first is just to do it in air. So we can cross a few femtosecond beams in air. That's an image of what the tracks of the beam look like, and that will create a grating. It won't be a very good grating, but it's pretty easy to, well, I'm not going to say pretty easy. Relative to the other methods, it's easy to create in the laboratory. You can do it on an open tabletop. The second approach is to take advantage of avalanche ionization. So using sort of 100 picosecond beams, this allows us to, with more efficiency than sort of a direct femtosecond field ionized approach, create a grating. And this has gotten us to sort of the highest efficiencies, although there are some other limitations with this approach. And finally, I'll talk about how the jump in performance that we get when going from atmospheric air to a more carefully controlled vacuum environment and a gas cell, and having control over the initial density of gas that we're working with allows us to go from having a sort of an interesting physical effect to something that has optical type performance. So in air, what we do is take two femtosecond beams, 400 nanometer pump beams, and cross them to create a grating. And then we probe that grating with an 800 nanometer probe beam. The reason we've chosen those wavelengths is because second harmonic is the easiest additional wavelength to get from a system like this. So the laser produces 800. It's easiest to get 400. And we wanted a different wavelength because that means that the pump and the probe beam are at different angles of incidence. So we can separate those beams out spatially as well as spectrally and get a little bit of a better idea of what's going on. So this is relatively straightforward. Efficiencies tend to be fairly low, and beam quality tends to be extremely poor. So we're in a geometry like this. The grating shape is determined by the overlap of two beams. So that is not a transmission grating or a reflection grating. It's that arbitrary grating that I talked about before. And as a result, there are fairly low limits on the maximum efficiency that you can get, even if everything works perfectly. And the beams that you produce tend to be pretty messy. So you can see this is, the top right image is like the best possible performance we ever saw from a grating like this, which is around in the 30 to 40% efficiency range. And in most cases, we end up with diffracted beams that are extremely distorted. So they're curved, they're spread out in space. There's evidence of multiple filamentation in this extended region. So the spatial quality is poor. It's not really useful afterwards, but there is diffraction going on. The grating does work as a grating. It just doesn't work as a very good grating. But we can use this to sort of start to get a handle on some of the initial dynamics of the behavior. So we can measure the plasma density, and what you're seeing here is how the plasma density evolves in time. So when we turn on the pump beams, or when the pump beams pass through this interaction volume, there's an initial turn on in the plasma density. And then when we send a sufficiently intense probe beam through, there's another jump in our measured plasma density. So in air, we're sort of getting plasma densities in the range of up to 10 to the 19 per centimeter cubed. You can see that the grating turn-on is fairly fast, less than a picosecond, and the lifetime is relatively long compared to the turn-on. So tens to maybe 100 picoseconds of lifetime for this type of grating. We can directly measure the lifetime of the grating, not just by looking at how the density evolves in time, but how the diffraction efficiency of the grating changes as the probe is delayed in time. So you can see that this sort of matches our expectation. There's a relatively fast turn-on in diffraction efficiency. If the probe arrives before the pumps, nothing is diffracted because no grating exists. But if it arrives afterwards, there's some kind of tens of picosecond lifetime before the grating structure has disappeared, either due to recombination or diffusion of the plasma into the neutral gas. So now we want to move on away from air into a regime where we're creating a finite grating. And the first way that we're going to do this is to create a finite volume grating in a gas jet using avalanche ionization. So now we've switched from using sort of 30 femtosecond, 800 nanometer pump beams to 1 micron, 120 picosecond pump beams. And the advantage of using these pump beams is that we are a little bit more efficient at coupling pump beam energy into the plasma. This may be a better long-term way of improving the overall efficiency of our optic. There are some disadvantages as well. It takes the turn-on time is a lot longer. There is a more limited regime potentially where the grating is useful. But in this configuration, using now a almost 4 micron probe beam, we can also create a grating and measure some of the performance of it. I will comment that the 4 micron probe beam is useful for us because it requires less plasma to have an efficient interaction. So it's, in some sense, it's a little bit unfair. We're making the problem easier for ourselves than it would be at 800 nanometer, which is the wavelength we want to get to. But it also allows us to explore what does it look like if we're getting high efficiency diffraction from a grating a little bit more easily. So what we did here is we started with a jet, so a sort of millimeter scale jet of gas. Here it's a jet of CO2 into air, so actually not under vacuum. And we're taking advantage of the fact that CO2 has a lower ionization threshold than air. So even though there is gas everywhere, we only get plasma where there's carbon dioxide, not where there's air. So this does give us the finite grating length that we're trying to study. And in this kind of configuration, we can boost the efficiency of diffraction that we see to the point where we actually have more energy in our diffracted beam than in our undiffracted beam. We can get sort of past this, this threshold, and in this regime, the diffraction process can no longer be treated as small. So we're no longer in a regime where diffraction of light away from our beam that's going through the grating is not affecting that diffracted beam. And so we start to see some things, changes in the shapes of these beams, which you can already see are a little bit higher quality than what we were doing in pure air. But we're getting into a regime that we want to ultimately operate in, where most of the beam is being diffracted and not a lot of it is being left behind. In the process of these experiments, we made some adjustments and went from using carbon dioxide in air to creating an argon cluster jet under vacuum. And this turned out to be an extremely efficient way of creating a grating, given the laser that we had available at this facility. And here, we were able to get up to about 60% of the instant energy to be diffracted into a beam with sort of a ratio of diffracted to undiffracted of almost 9:1. So we are losing energy in this particular configuration. Most of it appears to be lost to absorption rather than to light that is not diffracted. So we're now in a regime where almost no light is left in the undiffracted beam. Obviously, we would like to not be losing, 30% of our energy absorbed in the plasma, but it is a step in the right direction. And it's certainly a lot better than, 1% diffraction efficiency or 5% diffraction efficiency. So this configuration allows us to study some of the different dynamics of the process in an avalanche grating. So because we're using hundreds of picosecond pump beams, and because the grating is associated with an ionization process that doesn't happen within 10 femtoseconds, we see that the grating formation time is a little bit longer. So we have a slower increase in this diffraction efficiency, a lifetime that's still kind of on the scale of tens to hundreds of picoseconds, but some kind of reasonable behavior and some lifetime over which the grating is useful. So you can see as we go to later times, the grating starts to get a little bit messed up and the beam that is diffracted through it no longer has that nice spatial mode. But we do have some region where we have a reasonable high quality interaction. And what's important ultimately is that the beam that comes out of this interaction is focusable. That's what we want, enough spatial quality that we get a good focal spot from the beam. And so what you see here are our measurements of the what the beam quality of the original probe beam is, so before it goes through the grating, and the beam quality that we're able to achieve at a focal spot after the grating. And so there is some lifetime associated with this. At short times after the grating is created, we can get this kind of quality at top. At longer times, as the grating starts to get a little bit messed up, the focal spots that come out look like those at the bottom. And this tells us that we can actually see when we're creating a bad focal spot. It's not some filtering process that we're actually doing. But if we're careful about how we set up these gratings, it is possible to get a useful beam out of them with some kind of non-negligible efficiency. As a side note, we kind of want to think about, we made the claim that plasmas had much higher damage thresholds than solid optics. This is still a little bit of an area where we don't have a lot of measurements yet, but we can start to try and attack the question of what are the thresholds on these optics actually look like. And so the top left is a simulation. This is at low intensity on the left, so you can kind of see there's a grating structure there. And as we increase the probe beam, eventually what you're seeing is the probe creates so much of its own plasma that that original grating structure isn't really important anymore. So it's creating a ton of plasma and you don't have a grating, and so you're not going to get good diffraction. At the right, you can see that in this particular extremely small grating that we were creating, there's some kind of decrease in performance as we increase the probe energy. And so this configuration here corresponds to intensities about 10 to the 14, where we start to see a drop in performance associated with increasing the intensity of the probe. Now, we expect that to be fairly low for this type of optic because we're using easily ionized materials intentionally to make it easy to create the grating. There are, in principle, ways to make gratings that are more resilient to high probe intensity than this, even using the ionization mechanism. But there's a little bit of trade-off between how easy it is to create the grating and how resilient the grating is. And with the lasers that we currently have available, we're generally operating in the make the grating as easily as possible regime rather than try to increase that damage threshold. Now, controlling 3.9 micron light, because it has a lower plasma critical density, is a much easier problem than controlling 800 nanometer light or 1 micron light. But those are the wavelengths that we actually want to be able to get control over in order to build a higher power laser system, because those are the wavelengths that our systems operate at. So we're going to return to this femtosecond pulse, femtosecond probe configuration, but now using a gas cell. So we are setting up a gas cell inside a vacuum chamber with 2 apertures for the beams to pass through. And this gives us some kind of restricted volume of gas. And if you look very carefully at the shadow graph image in the middle, you can see some horizontal lines going across, which are is the index modulation associated with that grating. It may not show up very well on the screen, but they are there, I promise. So this configuration allows us to make some fairly careful measurements of how the behavior of the grating matches with our theoretical expectations. So on the left is that plot that I showed of how efficiency drops as you move away from the Bragg angle. On the right is our measurement of how the diffraction efficiency drops as we change the angle of incidence. So we're changing the angle of incidence of the probe beam on the grating. And you can see that there's this decrease in diffraction efficiency of the first order as we go away from the angle being exactly the Bragg angle. What's interesting in experiment is that we can also observe second order diffraction from the grating. So this is due to the fact that our grating is not perfectly sinusoidal. It has some higher order frequency components in it, and we can get higher order diffraction from those frequency components if we go to large enough angles. So this actually gives us a lot of information about what the specific spatial structure of that grating is. But you can see that this sort of performance allows us to understand our gratings from sort of pure optic theory. We actually can throw away the plasma physics for a minute and consider this purely as an optic, which is our ultimate goal when we're trying to build, plasma optics. We want to be at the point where they act as optics and we don't have to worry too much about the plasma. So you can see that the other part of this is trying to get a handle of exactly what is going on inside these gratings. And at the left is an interferometry image at quite high resolution showing that we can pick out the grating structure. So this is the horizontal lines are the fringes associated with the grating itself. Their spacing depends on the angle of incidence, the crossing angle of those two pump beams, in a way that's very closely matched with theory. And we can measure this grating structure over many shots and observe how it behaves, have some kind of stability of the grating. We're still sort of improving this. But these are gratings that we can create 10 times a second with some kind of reasonable reproducibility. And by reasonable reproducibility, I mean that there is some kind of diffracted beam most of the time. So here are the beam profiles for the near field and the focus beam that we get from this kind of grating. This, as if you remember what the atmospheric air grating looked like, these are much better quality. So we now have a beam that doesn't lose its spatial quality as we go through the beam. We can bring it to a high quality focal spot after the interaction. And we can run this interaction for hours at a time with sort of fluctuating, but more or less stable performance. Now, you can see that here, the majority of the shots are sort of in a 10 to 20% range of energy in the diffracted beam. That's kind of the scale of the fluctuation. Some of them have almost twice the energy and some have almost zero energy. But there is this ability to run this optic for an extended duration of time. It's not just a one-off experiment. We can also, at this point, this is a beam. It really is a beam that you can align in the laboratory. So you can stick an IR card in it and you'll see the beam traveling through your beam path after the interaction. And what this allows us to do is do things like measure the temporal contrast of the grating. So this is a Sequoia measurement of the temporal contrast of the beam. If you've done these before, you know they take sort of hours to scan across the beams, so you need some kind of reasonable stability in your system to even make this kind of measurement. And so what we're showing here is that we've taken our incident probe beam, we've deliberately spoiled its contrast by adding a prepulse. So you're seeing the temporal structure of this high-intensity probe beam in time with a sort of a 5% prepulse added to it and some additional pulses that are added as a result of that prepulse being there. And we can show that going through this grating, as you might expect, increases the temporal contrast of our beam by at least 5 orders of magnitude. So in comparison, a plasma mirror generally gives you 2 or maybe 3 orders of magnitude of contrast improvement. And the reason for that is a plasma mirror sends light in a preferential direction before the plasma mirror is actually created. Here, we don't have a grating before we create it. It's just gas. There's no preferential direction for the light to travel in. So those pre-pulses, the amount of light from those pre-pulses that travels along your final path of your diffracted beam is extremely small. And so here we're running into a measurement limit. We know it's at least 5 orders of magnitude. It is possible that it's somewhat more than that. So in the final few minutes that I have here today, I'm going to talk a little bit about the applications that we have in mind for these optics and the kind of parameters that we are working towards. So you're familiar with chirped pulse amplification, which is the standard way to create high power femtosecond pulses. So we send our beam through a stretcher, stretch it out, amplify it, and then recompress to get our compressed amplified pulse. The problem here is that this final compressor grating sees the full compressed power of the beam. So it has to be able to withstand the full intensity of the beam. We can, in principle, take advantage of the fact that transmissive gratings are dispersive to try and replace that final grating with a plasma. So we know that there's some dispersion associated with a transmission grating. We have some constraints on that. So if we have a particular spectral bandwidth, we want to get as large a dispersion as possible to enable efficient compression within a fixed amount of space. When we're designing a grating, we find that using a larger angle of incidence reduces the bandwidth that the grating can tolerate, but it increases the angular dispersion available to us over that bandwidth. A larger plasma density is generally good for us because it gives us more bandwidth to work with. The problem is that getting higher density modulations in our grating is harder. It's harder to make a high quality grating with a higher plasma density. So we have these constraints on the type of grating that we would like to get to design a laser system. And so we can put these constraints together. And what we find is that the issue is that a plasma grating is like the ones that we're creating in the lab, generally does not give us as much dispersion as a traditional solid state grating. That means that the two final gratings in our compressor would have to be extremely far apart in order to pick up enough path length difference to compress a nanosecond pulse down to 10 femtoseconds or 20 femtoseconds. In this chart here, what we're showing is the a plot of laser bandwidth and Bragg angle and the amount of compression that allows in a given amount of space, or how much space it takes to do a given amount of compression. So this sort of B in distance versus tau in picoseconds means that if you had a 1 nanosecond pulse, so 1,000 picosecond pulse, and you wanted to compress it, and you had a bandwidth of 0.1 and a grating angle of 10, that would put you on that black line of where it says 30. Now that's saying if you have a plasma grating where you have an index modulation of 0.005, you can create the grating you need to compress this pulse. It'll take 30 millimeters for every picosecond that you want to compress. So that means 30 meters for a nanosecond laser pulse, 1,000 picoseconds times 30. So 30 meters for a compressor is a little bit big. We've made our grating really small, but now our compressor is huge, and that doesn't help very much either. What we find is that we're kind of running into this problem for full-scale compression, regardless of the sort of reasonable plasma modulations that we can get, which is about 1%, so the 0.01 line. To get around this, what we have proposed is using a dual-stage compressor. So rather than trying to do the whole nanosecond to 20 femtosecond compression in a single step, we use solid state gratings to get us from a nanosecond to about 10 picoseconds. And in this regime, the laser damage is mostly coming from the energy of the pulse rather than the peak intensity of the pulse, if we're talking about 100 picoseconds and longer. And so we can keep our compressor relatively compact and the gratings relatively small if we don't compress all the way to 20 femtoseconds in our solid state optics. Then we have a 10 picosecond pulse in a second stage plasma compressor. And now this becomes a much easier problem because we're only trying to compress from 10 picoseconds down to 20 femtoseconds. So 10 picoseconds times 30 is only 300 millimeters of distance, which is the size of a standard sort of terawatt to petawatt scale compressor. So using a dual stage system like this, we can actually shrink, keep the largest optics somewhere between 100 and 1,000 times smaller, while not increasing the overall footprint of our laser. And what's promising here is that our experimental measurements of things like the dispersion of our gratings matches very well with what our theory, simple optical theory, predicts that dispersion should be. So we have experimental evidence that we can create dispersive gratings with the kind of properties that we would need to build a system like this. But we have a lot of work still to do in terms of getting the efficiency and the stability to where they would need for a system like this based on this technology to be useful. And this is just some simulations showing that computationally the performance through a grating, an ideally created grating, can be high enough to support these sorts of pulse durations. So gratings are not the only things that we can create. We can use a very similar process to create plasma lenses. So if instead of crossing two pump beams at an angle, we cross two pump beams with different distances from focus, their interference pattern will be a series of rings rather than a one-dimensional grating. And a diffraction pattern like this is a zone plate. And it allows us to think about focusing extremely high power lasers, not just changing their direction or adding dispersion. And so this is important because if our laser puts out a very small diameter beam with a lot of power that can only be handled by a plasma, we do also need ways to manipulate that and focus it onto our target and that kind of thing. Any standard mirror we put in that beam will also get burned. So we can, at least in principle, create the other kinds of optics that we need through very similar mechanisms like this. And again, the theoretical efficiency of a lens like this is not 100%. It's a little bit lower, but it is high enough to be potentially useful. So, and then the final application is that we can think about making transient optics of this type for things like protection of inertial fusion energy systems. So we can use a grating probably for this type of laser based on gas optics rather than plasma, rather than ionization optics. But it allows us to turn a beam and keep all of our final glass optics out of the line of sight of our laser. So we can do things like turn and focus a beam without placing any solid optics in the debris or X-ray flux regions of what might be a high repetition rate, high damage environment. So I'd just like to acknowledge some of the people who I have been working in this area, some of the results that I've shown, including some people from here, in particular Pierre Michel. And with that, I will leave this summary slide up, and I am happy to answer any questions.
Thank you. We already have a couple of questions from online.
Sure.
So the first is from Bob Kirkwood. says, if the efficiency of a gas or plasma optic is defined as the energy in the desired output, a beam divided by the total optical energy used in all the input beams, including pumps and seed, how efficient are the optics you describe? And or how efficient do you think they could be if optimized?
Right. So we have two different measurements of efficiency, only one of which I talked about, which is just sort of, given that your optic exists and you try to send light through it, how much does what you want? And then the one that Bob is asking about is, if you include the additional energy it took to actually create the optic, how much will go through? Now, we are focusing on mechanisms where we think there's good evidence that the energy required to create the optic can at least be in principle much smaller than the energy that is controlled by that optic. So somewhere, the target is that energy is between 1 and 10% of what can be controlled, so that it doesn't, if it takes 200% of the energy that you're controlling to create the optic, then you're not gaining very much. There are a few approaches that we have in mind that would allow us to do it. For something like the ponderomotive gratings, like computationally, you can show that it's possible to create the grating with a lot less energy than it takes to destroy the grating. So you can control a lot more energy than it took to create. And so for that computational simulation, that efficiency, like the total efficiency, including all of the energy in, is something like 85%. Now, experimentally, things get a little harder. We have some ideas about how to do it, but we have mostly, because the beams available to us have mostly been limited by the facilities that are available, we're often using pump beams that are not very efficient for what we're trying to do. So our actual efficiency for some of this, like the gas cell experiments at 800 nanometers, the efficiency of diffracting the probe beam might be 30%. We're using about as much energy in the pump beams as is in the probe. So the overall efficiency is closer to 10% in that case. But we do think there is a path to get higher. And we're only pursuing this because we're reasonably convinced that there is a path to get that efficiency higher.
Thank you. There's also a question from Isaac Bass. How do plasma gratings contrast with conventional acousto-optic deflectors?
So they are, in some sense, it can be a similar idea. These particular gratings, we can get much larger modulations in the index of refraction than an acousto-optic modulator. The gas gratings that have been demonstrated, the change in density is almost 100%. So like you're creating, and it's not just sort of a 1% fluctuation in the gas density. You're really going from like vacuum to twice atmospheric density. It doesn't last very long, but that the ability to create a large modulation in the index of refraction is very important for being able to efficiently control these probe beams, especially if we're talking about short pulses with broad bandwidths. So the sort of standard way of doing acousto-optic modulation, even if we were to do it in a gas, generally is not going to give us access to the same strength of control over the beam.
Great. Thank you. And there's another question online from Jean-Luc Vey. How challenging are the PIC simulations? Any challenge related to the computational cost, numerical effects, or other?
So these, there's some issues with using PIC for ionization optics. Like there's a lot of neutral gas physics that is important that isn't really captured by PIC. But for the ponderomotive optics, we can use PIC with some degree of confidence. This is a 2D simulation here. It's sort of expensive, but not prohibitively. So doing like 3D calculations of something like a lens is definitely more expensive than I would like it to be. We've done it. We've done PIC simulations of transit through a lens, but we're sort of we can't make a lens as large as we want. We can't simulate a millimeter scale lens. We're kind of at the few hundred micron scale. So there are things that we cannot do that we would like to be able to do in terms of computational expense, but most of the questions we can at least get an answer for, even if things are a little bit scaled down.
Thanks.
Pre-pulse, oh, sorry, the mic. I had a question about the pre-pulse suppression. So with a plasma mirror, the way I understand it, that if your energy is hitting the mirror and is below the intensity threshold for ionization, it passes straight through. And then when the intensity surpasses that, it ionizes and reflects. In this situation, you're already ionized, right?
No. So what you're seeing is the pump beams ionize the probe. So it is ionized when the probe arrives, but the probe is arriving, it can arrive 100 femtoseconds after the pump beams.
If the jitter is that good.
So these are all optically synchronized.
Okay.
In the sense that it's all derived from the same beam.
Okay, so your grating pumps are split off from your main.
Yeah.
Main
so
okay.
the way that we set it up here, for example, is the ideal configuration is you'd pick 10% off of the main beam and use that to create your grating, and you have to adjust the geometry a little bit so that it arrives slightly before. But that's more or less what we're doing in experiment. It can't be two separate laser systems for this.
So then on the time scales of the gratings, because you said the ponderomotive gratings appear at femtosecond levels, but the ionization ones take picoseconds, right, to grow and to form.
So the ponderomotive ones take picoseconds to form.
Okay.
The ionization ones take as long as the ionization process.
Okay.
The pump beams are only 25, 30 femtoseconds long. It's all pretty much happening within the pump beam.
I see.
It's, sometimes shorter than that. We kind of, when we're directly measuring something like the contrast improvement, what we can say is that we're cleaning before negative 500 femtoseconds. We don't really have good measurements closer than that for that sort of autocorrelation measurement. But certainly we see that improvement up to 500 femtoseconds before the arrival of the main probe pulse.
Okay.
Thank you. Just one last question from Roger Falcone. Is there a simple relation between the power and energy handling capability of plasma optics and power and energy needed to create the plasma optic?
The answer is no, it's not simple. So the mechanisms that I presented are ones where we think that either we need less power than we can control or less energy to create the optic than we can control, or both. The relationship between those depends strongly on the mechanism. It can depend strongly on the wavelength relationship between the pump and the probe beam and the material. And we don't know for all configurations what that looks like yet. So I guess the short answer is it's not an easy answer, and there's still a lot of unknowns. But it seems like there are, what we're targeting is things that allow us to have the handling capacity be larger than the creation capacity. So this, for example, the pump intensity is about 2 orders lower than the orders of magnitude lower than the probe intensity that was controlled by the grating. So in terms of power, we're gaining 2 orders of magnitude. We used more energy in the pump beams. We used a longer duration pump beam than the probe. So the energy balance is not quite as favorable as the power balance, but I think we're still positive here. So we were taking advantage of the fact that these ponderomotive gratings, we can drive them fairly weakly and then give them time to evolve. And then the probe beam is so short that even though it's higher power, not that much happens in 20 femtoseconds compared to the 2 picoseconds over which the grating evolved. And so that gives us that favorable power balance for this type of grating.
Okay. Thank you very much. Let's thank our speaker again. So long, everybody. I hope you have a great rest of your day and hope to see you next time.